Okay, so today we're going to talk about unitary transformations and unitary operators. And the ultimate goal of this topic is really to understand the machinery that we're going to use for taking our light matter coupling Hamiltonian, which we've been calling the P dot A Hamiltonian, and turning this into ultimately a different representation. We're actually just going to look in detail about a single unitary transformation, which actually what I should really write is this single unitary transformation that will apply is going to get us from our so-called P dot A Hamiltonian to this other Hamiltonian called D dot E. There's going to be an additional unitary transformation, which is going to take us from the D dot E to the Polyfeuritz Hamiltonian. And we actually will sort of spend a little bit less time on that second unitary transformation, but nevertheless, it's important. So this unitary transformation that we'll actually talk about in more detail is called the Power-Zenar-Woolley transformation, or PZW transformation. And one of the things that we're going to see is that it is going to be a transformation which shifts both the matter momentum operator and the photon momentum operator. So one of the things that we can actually say in general is that unitary transformations can be used to apply shifts in quantum mechanics. And so we'll definitely see how that works as we go along. We're also going to write down a few other properties of unitary operators and unitary transformations to begin with. But the real reason that we're going to do any of this, right? And so I'll just remind you a couple of features of this P dot A Hamiltonian. So in this P dot A Hamiltonian, the light matter coupling occurs through the matter momentum operator, and the vector potential of the photon. And so one of the things that is important about the matter momentum operator is that a good basis for the matter momentum operator is a delocalized basis. So think about the plane waves, for example, as those are the eigenstates of the momentum operator, and they're very delocalized in space. Okay, so now one of the things that is going to happen as a result of our unitary transformations is we're actually going to change ourselves to a representation where the light matter coupling occurs through different operators. In particular, the light matter coupling after this unitary transformation is going to occur through the dipole operator of the matter and the electric field of the photon. And so now the reason why that is important or convenient is that you can actually think of the dipole operator as being kind of conjugate to the momentum operator. So the dipole operator is really the position operator of the momentum multiplied by charge. So if I think about what is the dipole operator, right? It's something like Z, where Z is the charge of the matter times its position operator, okay? And so as opposed to P hat, right? So P hat, is minus I H bar d dx. Okay, so these are really conjugate of each other. And so what that means, if the P hat eigenstates are very delocalized, and that makes a good basis for p hat, a delocalized basis, then that means the eigenstates of mu hat are very localized. All right, they're the same as the eigenstates of the position operator. They're very localized functions. Delta functions are basically the eigenstates of the position operator. Okay, so basically, just what we have here is good basis is a delocalized basis for p hat, whereas for mu hat, a good basis is a localized basis. And so that's important because usually when we're dealing with molecules, right, we like to have localized bases. And when you're running quantum chemistry calculations, we're going to be using Gaussian basis sets, and those are really localized bases. And so it actually is very convenient then to have your light matter coupling occur through an operator for which a localized basis is a good one. It just makes your calculations more convenient. You don't need as many basis functions to sort of converge to some sort of complete basis set limit. You would need a lot of localized basis functions to represent sort of an appropriate delocalized basis for p hat. So that's just an important difference. Okay. So that's the motivation. So let's just spend a few minutes talking a little bit about what a unitary operator is. Okay. So what is a unitary operator? All right, so a unitary operator is defined as one, so I can say U hat is unitary if the adjoint of U is equal to the inverse of U. Okay, so this is sort of a really special operator where its adjoint is equal to its inverse. Okay, so then what does that imply? Well, if I take products of the operators like this, mu dagger, so take mu times its own adjoint, which is that product is going to be the same thing as mu adjoint times mu. And both of these would be the same thing as taking mu times its own inverse. And so what this gives us is an identity operator always, okay? So that is basically the definition of a unitary operator. And one of the things that we'll see that we can do then is actually we can always define a unitary operator in the following way. So basically what I'll write is I'll take an exponential of an operator, which is Hermitian, and multiply it by the imaginary unit. So we can define unitary operators as exponentials of Hermitian matrices, Hermitian operators multiplied by I. Okay, so in other words, I can say U hat is equal to E raised to the I A hat. Okay, and where A hat is Hermitian. So what does that mean is that A hat dagger is equal to A hat, right? So that means what happens if oops, I wanted to say positive I, sorry about that. U hat is equal to E to the I A hat. And so then if I take the adjoint of that operator. So take mu dagger, right? What am I going to get? E to the I complex conjugate A hat adjoint, right? I'm going to take the complex conjugate of I, and I'm going to take the adjoint of A hat. And so what that's going to give me is E to the minus I A hat, right? Why do I get E to the minus I A hat? Well, minus I is the complex conjugate of I, and A dagger is equal to itself because A is Hermitian, okay? And so the other way of saying this, right, is, okay, well, I've taken the dagger of this operator and I've gotten its inverse, right? Why? Because if I were to multiply E to the I A with E to the minus I A hat, right, then what I get is E to the I minus I A hat, which is E to the 0, which is A hat, which is the identity operator. Okay. So that's all there is to it. So, so that is one way that we can write a unitary operator. Okay. So now let's look at a few of the properties that we get out of unitary operators when we act on states. Okay. So basically, what we're going to do is we're going to define, so let's take the action of unitary operators on some ket, which I'll call psi1. Okay. So in particular, what I'm going to say is that the unitary transformation of ket psi1, I'm going to get a new ket back, and I'm just going to call that ket psi1 prime. Okay. So importantly, right, this unitary transformation is going to produce a new ket. All right, so it's been rotated. If you want to think about this as a vector, right? So it's been rotated relative to the original ket. But one of the things that we'll see, in fact, is that its length has not changed. And so this is kind of an interesting contrast to what we have seen when we have taken a Hermitian operator and acted on one of its eigenstates. So that's not really uniquely a property of Hermitian operators or anything, but that's just been a context that we've seen a lot, is that we've taken a Hermitian operator like the energy operator or the momentum operator or the kinetic energy operator or something like that, and we've acted on one of its eigenstates, right? We get the same state back, so it points along the same direction, but it's been scaled by an eigenvalue, right? So it's lengthened or shortened. So this is a little different. We're basically claiming here, okay, I'm going to take this operator mu or u hat, I'm going to act on this ket, and I'm going to produce a new ket. It's going to point along a different direction, but it's actually going to have the same length, right? Its magnitude hasn't changed. So can we actually demonstrate that its magnitude hasn't changed? So in fact, we can, right? So if I'm going to define my unitary transformed ket, psi1 prime ket like this, then its corresponding bra, right? Basically, remember, the bra is the adjoint of the ket. So what do I do, right? I have to take, I need to do a transformation on the bra of psi1 with that same unitary operator's adjoint, right? So now I have to do mu hat dagger acting on bra psi 1 to get bra psi 1 prime, okay? So let's now take the bracket of psi 1 prime as the bra with psi 1 prime as the ket. And by the way that we have defined psi 1 prime, this can be equal to psi 1 on the bra with u hat dagger acting on it. And then psi 1 prime on the ket is equal to u hat acting on psi 1 on the ket, right? And then I can look at what operators are sandwiched between the bra and the ket. It's u dagger times u, which is the identity. So at the end of the day, this is just going to give us psi 1 on the bra, psi 1 on the ket, okay? And so this is to say that whatever the original magnitude of psi 1 was, that will be the same as the magnitude of psi 1 prime, okay? And just more generally, what you can say is that unitary transformations preserve the inner products of the states they act on. Okay. So let's also do the same thing when I have two different states. So let's actually think about psi n, psi m versus psi n prime, psi m prime, right? And so we can use exactly the same kind of rationale as before, right? So we can say that psi n prime is the same thing as psi n on the bra with u hat dagger, and psi n m prime on the ket is u hat acting on psi m, right? Which is equal to psi n on the bra, identity matrix, psi m on the ket, which is equal to psi n on the bra, psi m on the ket. That's it, right? All right. So the next thing that we can look at is actually how the expectation values and eigenvalues of operators will behave after being transformed. So we're going to pick that up in the next video.